Welcome to A-Level and EP Physics. In today's lesson, we will discuss past paper questions from October-November 2023, Paper 4, Variant 1. In today's lesson, our main focus will be on nuclear physics and medical physics. As always we do, we will discuss these questions in detail so you can improve your conceptual understanding of these two topics and also you can have better understanding of these exam questions. Let's study together, let's improve together. Question 9 part A says, state what is meant by nuclear fusion. Nuclear fusion simply means that when two lighter nuclei combine together and they form a heavier nucleus. This process of combining lighter nuclei to form a heavier nucleus is called nuclear fusion. And in this process, mass will be converted into energy. So a lot of energy will be releasing in this process. Let me explain you this one in a little bit better way. You can simply imagine we have this one nucleus and this is another nucleus. These two nuclei, they combine together, they form a heavier nucleus. Let's say mass of this nucleus is m, mass of this nucleus is m, and mass of this nucleus is capital M. And also in this process, energy will be released. And this energy release, this is equal to the mass difference between parent nuclei and daughter product. So we can simply say m plus m minus capital M, this is equal to delta M. And delta M is the mass defect, or we can say this is mass difference. You can also say this is mass deficit. So how we can calculate this energy released? So energy released, we can say delta E. This is equal to delta M times c square. So this is how we can calculate energy released. And this energy is equal to the mass difference times c square, mean how much mass has been converted into energy times c square. We can calculate energy released. And this energy will be released in form of kinetic energy of daughter products. So we can say daughter products plus gamma radiations. Simply you can say plus EM radiations. So this is how this energy will be released. It will be released in this form. So these are the points you need to understand about nuclear fusion. Now let me show you the answer, how you can write down your answer. In your answer you can mention these points. You can simply say is the process by which two lighter nuclei combine to form a single heavier nucleus while releasing massive amounts of energy. If you write down this one, you will get 2 marks. Part B says on figure 9.1, sketch the variation of binding energy per nucleon with nucleon number capital A for values of A between 1 and 250. This question is a typical question. You need to understand how to sketch binding energy per nucleon against nucleon number or mass number curve. And we also need to understand that iron 56, it has the highest value of binding energy per nucleon, Fe56. So it has maximum value, we can say maximum value of binding energy per nucleon. So this is one thing very important you need to understand. So that's the reason iron 56, this one is the most stable element. So this is most stable element, and that's the reason we have a lot of iron on our planet. So we have abundance of iron 56 because it's the most stable element. So we can also say we have abundance of iron because iron is the most stable element. Now keeping these points in our mind, we can sketch the curve. So simply we can start from here. So it will go sharply up and it will reach the peak, and after that it will go down. So iron 56 is located somewhere here. So we can say this is Fe56 because Fe56 is the most stable element. If the binding energy per nucleon is greater, it means element is more stable, not binding energy per nucleon. So you have to be very clear. Binding energy per nucleon, if this is greater, it means that element is stable, not binding energy. Binding energy not linked with stability. Binding energy per nucleon. Part C says on your line in figure 9.1 label a point X that could represent a nucleus that undergoes alpha decay. Most of the atoms with atomic number greater than 81, they undergo alpha decay. So simply we can say for alpha decay, atomic number if greater than 81, most of the element they decay by alpha decay. So simply we have to mark here, so we can mark round about here. So this point is point X. For the second part, we need to mark a point Y that could represent a nucleus that undergoes nuclear fusion. For nuclear fusion, we have already discussed lighter nuclei. They undergo nuclear fusion. So we can simply write on here lighter nuclei. So lighter nuclei you can simply mark here at the beginning of the curve. You can simply mark. So this point is Y. So this is how you need to mark these 2 points on this curve. Line mean curve. So this is curve. Part D says a nucleus capital Z undergoes nuclear fission to form strontium-93 and xenon-139 according to this equation. Table 9.1 shows the binding energies of these two daughter nuclei. The fission of 1 mole of Z releases 1.77 times 10 to 3 joules of energy. Determine the binding energy per nucleon in mega electron volts of Z. So simply we need to determine binding energy per nucleon of Z, and answer should be in mega electron volts. So how we can answer? So first thing you need to understand binding energy per nucleon. So this is what we need to determine for Z. So what do we need? So we need binding energy of one nucleus of Z, of one Z nucleus we can say. So we need binding energy of one Z nucleus. So we can say binding energy of one Z nucleus. So this is what we need, and we need to divide this one by total number of nucleons. So we can say we have to divide this one by number of nucleons. So this is what we need, divide by number of nucleons, and number of nucleons means is equal to the mass number, and mass number we can find out from here. So we have 1 here, so this is the mass number. So how we can find out value of this? So simply we can say in this case 1 plus mass number of Z, this has to be equal to 93 plus 139 plus 2. So we can find out mass number of Z, and mass number of Z in this case will be equal to 233. So this is the mass number of Z. So we can update here, we can write down here. So we have this one here. So this is the mass number. So we have determined the mass number. Now we need binding energy of one Z nucleus. But this energy is given to us for 1 mole. This is for 1 mole. This is energy released in 1 mole. Energy from one nucleus mean how much energy will be released. So we can say energy released in 1 decay. We can say energy released in 1 decay, or you can say energy released when 1 nucleus decay. That energy simply we can find out 1.77 times 10 to 13 divided by number of nuclei of Z, and that is equal to 1 Avogadro's number because this is 1 mole. So simply you need to divide this one by 6.02 times 10 to 23. So if we solve this one, we will get 2.94 times 10 to minus 11 joules. So this much energy is released when 1 nucleus of Z decay. And for this question, we have the binding energy of nucleus. We also have binding energy of this nucleus. This is the energy released we have calculated. So how we can calculate the binding energy of Z? Binding energy. Before we answer this question, you need to understand when binding energy increase, it means energy is released. So let me write down here. If binding energy increase, it means that energy is released. So we can say delta E release. So this is one point you need to understand. Energy will be released, and if binding energy decrease, it means energy has to be absorbed. Or we can say, another way to say this one is, we can also compare this one with mass. If delta M, or better way, let me compare this one. So we can say if the mass decrease, so we can say if the mass decrease, energy also will be released. So we can say delta E is released. So these two conditions are very important. You need to understand, if binding energy of products is greater than binding energy of reactants, means of parent nuclei, it means energy will be released. And if the binding energy of daughter nuclei is lower than binding energy of parent, it means energy has to be absorbed. So in this case, energy is released. So it means that the binding energy of daughter nuclei is greater than binding energy of Z. And individual particles like neutrons, they do not have binding energy. As I said before, that individual particles, they do not have binding energy, means no binding energy is associated with individual particles, because those individual particles, they are not in the nucleus, so there is no binding energy associated with individual particles. In this case, there is no binding energy associated with these two neutrons, and also no binding energy associated with this neutron. So how we can calculate energy released? At A2 level, you need to understand two methods to calculate energy released. One method, so I will be writing here, method one simply is, if you need to calculate energy release, this is based on mass. So simply you need to find out the mass difference, and you need to multiply with C square, so you can find out the energy released. But when you calculate this mass difference, you have to consider mass of individual particles as well. So total mass on the left side minus total mass on the right side. So you will find delta M. And the second way to calculate energy released is, so the second method, energy released, simply we can calculate by calculating the difference between binding energy on both sides. So energy released will be equal to the total binding energy. Let me write on here, total binding energy of products, means daughter nuclei. So we can say total binding energy of daughter nuclei. These points are very important, so you need to listen them carefully, and you need to understand. You don't need to watch a lot of videos, but the video you watch, that video must make sense to you. So that's the main point. So listen carefully and try to understand what I'm explaining you now. This is very important for your A2 physics, especially for nuclear physics. Total binding energy of daughter nuclei minus total binding energy, total BE, of parent nuclei or parent nucleus. So we can say parent nuclei or parent nucleus. So in this case, we have these two daughter, so these are our daughter nuclei, so these are daughter nuclei, and this is our parent nucleus. So the binding energy of these two we have, this is binding energy of one nucleus, this is binding energy of another nucleus. So simply we will write on here 1.25 plus we have 1.81, and both of them, they multiply with 10 to minus 10 minus binding energy of C. So here we have binding energy of C. So we need to find out binding energy of Z. But we have the energy released. So this is the energy released. Physics is beautiful. So try to understand. When these things, they will make sense to you, you will love physics. So try to understand. Physics is way of thinking. So develop your way of thinking. So binding energy released we have already, so we can write on here, this is 2.94 times 10 to minus 11. So we can find out binding energy of Z. So if we solve this one, we will get binding energy of Z. So in this case, binding energy of Z, if we do these calculations, we will get 2.77 times 10 to minus 10 joule. So this is binding energy of Z nucleus. So we can say binding energy of Z nucleus. So this is binding energy of one Z nucleus. So simply we can write on here 2.77 times 10 to minus 10. This is in joules. So if we solve this one, our answer will be in joules. But we want answer in mega electron volts. So we have to divide this one by 1.60 times 10 to minus 13. Now if we solve, your answer will be in mega electron volts, and your final answer will be 7.43 mega electron volts. So this is our final answer. And this is how you need to answer. So these two methods, please, are very important. I hope you have better understanding. If you are not clear, so look at this one. So energy released is equal to mass difference. You have to include mass of individual particle in your calculation. Mass of individual particles you have to include, you have to consider. But here, when you find energy release based on binding energy, you no need to consider binding energy of individual particles, because individual particles, there is no any associated binding energy with individual particles. So that is the main concept. I hope this question makes sense to you, and if these videos are helping you to improve your understanding of physics, and they are also helping you to understand these questions better, please like and subscribe, because your encouragement is very important to make more videos. And if you're looking for more resources, you can also join Patreon, and also by joining Patreon you can also support this work. Question 10 says, ultrasound and X-rays are types of wave that are used in medical diagnosis to form images of internal body structures. Complete table 10.1 to state for each type of wave the method of production of the wave, whether the wave that is detected and used to form the image is the wave that has been absorbed, reflected, or transmitted by the internal body structure. So first thing, method of production, ultrasound waves. How do we produce ultrasound wave? Just by vibrating quartz crystal. So simply we can say vibrating quartz crystal. So we can write on here vibrating quartz crystal. So quartz crystal, or simply you can say quartz crystal. How do we produce X-rays? When accelerated electrons are decelerated, we produce X-rays. Or simply you can say when accelerated electrons hit the metal target, we can produce X-rays. Detection means detected wave. In ultrasound, simply we have here, this is transducer, and here we have boundary between two different media. We will send ultrasound waves, and when they will reflect from this one, this reflected wave will be detected. So this reflected wave will be detected, and with the help of this one we can form ultrasound image. So simply we have to say here reflected wave is detected. And in case of X-rays, so here we have source of X-rays, we can say this is source of X-rays, and here we have the body, and at the end of this one here we have photographic plate. So this one is the plate, photographic plate. We will see the image on this one, and this is image on this plate is formed by transmitted wave, means waves will pass through this one and they will form the image here, transmitted. So simply you have to say transmitted wave. So detected wave is transmitted wave, means the X-rays that pass through the body of the patient. So this is how you can answer this question. Part B1 says, for one type of wave passing through tissue, the wave has 72% of its initial intensity after it has passed through 6.2 centimeters of the tissue. Calculate the linear attenuation coefficient of the tissue for this wave. So the best way to answer this question is, first of all, we can simply imagine this one is the tissue and the thickness of the tissue is given to us. So this is thickness of the tissue. Value of x is equal to 6.2 centimeters. Initial intensity, imagine that this is I naught. So the transmitted intensity in this case will be equal to 0.72 times I naught. And we need to calculate value of mu. So value of mu for the tissue we need to calculate. So simply we have to use IT, transmitted intensity. This one has to be equal to I naught e to the power of negative mu x, because intensity will decrease exponentially. So this is the point. So it will decrease exponentially. So we have to use this formula. IT we have, that is equal to 0.72 times I naught, and here we have I naught e to the power of negative mu x. So I naught we can cancel, so we left with 0.72. this is equal to e to the power of negative mu x. Now if we take natural log on both sides, we can say ln of 0.72, this will be equal to ln e to the power of negative mu x. Ln e is equal to 1, so we can write on here ln of 0.72. this is simply equal to negative mu x. So we need to find out value of mu. So mu will be equal to negative ln of 0.72 divided by x, and value of x we have, that is equal to 6.2 centimeters. Now if we solve this one, we will get 0.053 per centimeter. So this is the final answer. This is how you can calculate. Is a typical question. So this is how you can calculate. I hope this makes sense to you. You have to be very careful with this unit. As this unit is centimeter, so we got per centimeter. If this unit was meter, we will get per meter. Second part says, another wave of the same type as in B1 passes through 9.3 centimeters of the same tissue. As tissue is the same, it means that value of mu is equal to 0.053 per centimeter. So this is the value of mu. We need to calculate the percentage of the initial intensity of the wave that is attenuated. Attenuated means that absorbed. So absorbed by the tissue. And we need to understand initial intensity. This one has to be equal to the intensity absorbed, or you can say attenuated, plus intensity transmitted. So this is the main idea. So if you need to find I absorbed, so we can say I absorbed, this will be equal to I naught minus IT. So this is our main idea, main concept. So how we can calculate IT? So first of all, we can draw, this is our tissue, and the thickness of the tissue is given to us. Thickness of this one is 9.3 centimeters. So this is value of x. So we can say this is intensity of incident wave I naught, and the intensity of transmitted wave, let's say this is IT. So we can simply write down in this case IT, this one has to be equal to I naught e to the power of negative mu x. So we can write down IT by I naught, so we can find out the fraction of initial intensity that has been transmitted. So we can find out IT over I naught, and this is equal to e to the power of negative mu x. We have value of mu, that is 0.053, and value of x is also in centimeters, so you can use this one here, 9.3. E to the power has no unit. If you have e to the power of something, it has no unit. So this is the main concept. So if we solve this one, we will get in this case IT over I naught, that will be equal to 0.61. So it simply means that IT, from here we can say IT is equal to 0.61 of I naught. So this is IT is equal to 0.61 of I naught. So how about I absorb? So you can find out from here. So we have I naught minus we have 0.61 I naught. So from here we will get this will be 39 means 0.39. So this is 0.39 I naught. So this is I absorb means I attenuated. I absorb. So you got this one here. Question was asking you how much it is absorbed. So we got I absorb is equal to 0.39 of I naught. We need to convert this one into percentage. So simply we have to multiply this one by 100. So we can say percentage attenuated. So we can say percentage attenuated. So I absorb in percentage. So simply we can say percentage attenuated. So we can say percentage attenuated. This one has to be equal to 0.39 multiplied by 100. So this will be equal to 39% of I naught. 39% of I naught. You can also do this one in a little bit different way. So let me explain you that one. So here we can write down the percentage attenuated in a little bit different way. We can say percentage attenuated. This one has to be equal to 1.0 minus we have 0.61 means this value 0.61. So this is, and you can multiply this one with 100. So you will get here 39%. So this is how you can calculate. So this number is telling us 61% passes through the tissue and 39% is absorbed by the tissue. So this is how you can answer this question. I hope this question make better sense. And if you have any questions, please leave your questions in comments and I will try to answer as soon as possible. And if you're looking for extra resources, you can also join Patreon. On Patreon, you will find more resources. See you next video.